We are extraordinarily good at predicting the beginning of time. Ask an astrophysicist what happened in the first 3 minutes of the universe, and they can answer with astonishing precision. We know the temperature. We know the density. We know the nuclear reaction rates. We can calculate, almost to the decimal place, the exact ratio of hydrogen to helium that should exist across the observable universe. And when we look billions of light years away, when we analyze the oldest gas clouds in deep space, the numbers match. It is one of the greatest triumphs in the history of science. But there is a crack in that perfection. Right after hydrogen and helium in the periodic table sits lithium, a soft silver-white metal. According to our most trusted physical laws, the early universe should have produced a specific amount of lithium-7. But when we look for it, 2/3 of it is missing. This is not a rounding error. This is not observational noise. This is a factor of 3 discrepancy in one of the most precise theories ever constructed. This is the cosmological lithium problem, and it refuses to go away. To understand why this matters, we have to go back to when the universe was just 1 second old. At that moment, the cosmos was a plasma inferno, roughly 18 billion degrees Fahrenheit. Protons, neutrons, electrons, and radiation were locked in a violent equilibrium. No atoms could exist. Any attempt at structure was instantly torn apart by the heat. But the universe was expanding, and expansion means cooling. By the time the universe was about 1 minute old, the temperature had fallen to roughly 1.8 billion degrees Fahrenheit. Still unimaginably hot, but now low enough for the first stable nuclei to form. For the next 17 minutes, something extraordinary happened. The entire universe became a fusion reactor. This period is called Big Bang nucleosynthesis, BBN. Protons and neutrons began fusing. Most neutrons were quickly locked into helium-4. A trace amount formed deuterium, heavy hydrogen. Even smaller amounts produced helium-3. And in a tiny, exquisitely sensitive chain of reactions, lithium-7 was born. The key point is this. We do not guess these abundances. They depend primarily on one measurable number, the baryon to photon ratio. And that number has been independently measured with remarkable precision using the cosmic microwave background radiation, the afterglow of the Big Bang, mapped in detail by satellites like WMAP and Planck. When we plug that number into BBN calculations, the predicted hydrogen and helium abundances match observations almost perfectly. Deuterium? Also perfect. Lithium? Off by a factor of 3. In precision cosmology, that is enormous. So maybe we are looking in the wrong place. Lithium is fragile. Unlike helium, it does not survive extreme heat very well. At temperatures above about 4.5 million degrees Fahrenheit, lithium-7 is easily destroyed in stellar interiors through proton capture reactions. So perhaps stars burned it away. That was the leading explanation. In 1982, astronomers Monique and Francois Spite tested that idea by studying some of the oldest stars in the Milky Way, ancient metal-poor stars in the galactic halo. These stars formed early, from nearly pristine material, long before multiple generations of supernovae could contaminate them with heavier elements. If Big Bang nucleosynthesis is correct, these stars should preserve the primordial lithium abundance in their outer layers. What the Spites discovered was astonishing. Across a wide range of old halo stars, lithium abundance was almost identical. It did not vary with mass. It did not vary with temperature. It formed a flat line. This became known as the Spite Plateau. At first, it looked like confirmation of theory, a fossil imprint of the Big Bang. But the plateau sat far below the predicted value. Not slightly below, a full factor of 3 too low. If stars were randomly destroying lithium, you would expect scatter, some stars with more, some with less. Instead, the plateau is remarkably uniform. To explain this through stellar physics, every one of these ancient stars would have to destroy almost exactly the same fraction of lithium over billions of years. That level of fine-tuning is uncomfortable. So we face 2 possibilities. Either our models of stellar interiors are incomplete in a very specific and coordinated way, Or the early universe behaved differently than we think? The conservative camp focuses on stellar physics. Perhaps atomic diffusion slowly pulls lithium beneath the visible surface. Perhaps turbulent mixing redistributes it in ways we do not fully understand. Sophisticated stellar models incorporating diffusion and mixing can reduce the discrepancy somewhat, but not eliminate it cleanly. The radical camp looks earlier. What if something altered nuclear reaction pathways during those first minutes? Lithium-7 forms mainly through the decay of beryllium-7. If an unknown particle existed in the early universe, decaying dark matter for example, it could have modified the neutron-proton ratio or destroyed beryllium before it became lithium. Another possibility involves sterile neutrinos, hypothetical particles that interact only gravitationally. If present, they could have subtly changed the expansion rate of the universe during nucleosynthesis, shifting elemental yields. Even tiny variations in fundamental constants, such as the fine structure constant that governs electromagnetic interaction strength, would alter nuclear reaction rates. But here is the problem. We have no direct evidence for any of these solutions. Every proposed fix risks breaking something else. Change the expansion rate too much, and deuterium no longer matches observations. Modify nuclear cross-sections too aggressively, and helium abundance shifts out of range. The Big Bang model is tightly constrained. It works spectacularly well, except for lithium. And that makes this problem uniquely powerful. It is not chaos. It is not a vague anomaly. It is a precise, isolated failure inside an otherwise precise success. And that is often where revolutions begin. When you hold a lithium-ion battery in your phone, you are holding an element whose cosmic origin does not fully add up. The universe predicts more of it than we can find in its oldest stars. We have rechecked the reaction rates in nuclear laboratories. We have refined stellar atmosphere models. We have mapped the cosmic microwave background with exquisite detail. The gap persists. It forces humility. It reminds us that even our most elegant theories are provisional. If the answer lies in stellar interiors, we will uncover new layers of complexity in how stars evolve and mix their elements. If the answer lies in the first 3 minutes of cosmic history, then the lithium problem may be a doorway into physics beyond the standard model. Perhaps new particles, new symmetries, or new interactions. Right now, we do not know. And that uncertainty is not weakness. It is signal. The cosmological lithium problem sits at the boundary of what we understand. A quiet discrepancy embedded in the oldest light and the oldest stars. The Big Bang was not wrong, but it may not be complete. And sometimes it is the smallest missing piece that tells us the deepest truth. Veil origins, impossible truths.